Welcome back to part 7 on composition of functions. We're just looking at more examples in this video, and hopefully this will kind of help you start seeing the pattern that occurs when we're composing functions. Let's first define the domains of each of these functions. So the domain of f of x is all real numbers, or negative infinity to infinity. G of x, the domain is also all real numbers, or negative infinity to infinity. And h of x is also all real numbers, so domain for h of x is negative infinity to infinity. So the compositions should also be all real numbers, with the exception of a few unique scenarios. Let's take a look at g of f of x. When we use g of f of x, we're going to substitute f of x into g of x. We can rewrite this as an open space for f of x squared. Now, you can think of this as x being the number inside. However, we have to replace the variable with the function f. And f of x is x over x squared plus 8. We could simplify this by writing this as x squared over x squared plus 8 quantity squared, because we can distribute this 2 as an exponent. From here, we could FOIL the denominator because technically this denominator is the same as x squared plus 8 times x squared plus 8, but it's not necessary. When I look at the denominator, I see that there again are no restrictions on my domain because this x squared plus 8 has no points at which it will be 0. So we can say that the domain for g of f of x is negative infinity to infinity. You could also say the notation is all real numbers. This kind of double-lined r is defined as all real numbers. So now let's look at part B. We want h of g of x, or h composed with g of x. So my outermost function is h of x, and then g of x is being substituted in. This is going to give me an empty space where x was in the x minus 3 function, and within that function I'm going to substitute g of x. That means I can rewrite h of g of x as x squared minus 3. Again, the domain of this function is going to be all real numbers because there are no fractions with variables in the denominator that cause zeros, and there are no radicals. C is saying compose h with h of x, which is kind of weird to think about, but we're going to just do the same process as before. We're going to replace x with just open parentheses in h of x equals x minus 3. When we do that, we will have open paren, close paren, minus 3. Once we know where to substitute h of x into h of x, we're going to then put x minus 3 inside as well. We can simplify that, and we get x minus 6. The domain, again, has no restrictions, and we can write the interval from negative infinity to infinity. Now we need to find the composition of f of h of x. First, the outer function. We'll leave open spaces wherever there's a variable, and then substitute h of x, which is the x minus 3, inside. I will then simplify. In the numerator, we still just have x minus 3. In the denominator, however, remember x minus 3 squared is the same as x minus 3 times x minus 3, which means this is going to be x squared minus 6x plus 9 plus 8. If we simplify that further, we can combine the 9, and that will give us x minus 3 over x squared minus 6x plus 17. We should probably graph this denominator and just double check that it never has a value equal to 0 for any value of x. As you can see, I've entered the denominator, x squared minus 6x plus 17, into my calculator in y sub 1, or y equals. Now I hit the graph button. The window is in Z standard, and you can see that there's only a small little portion of the parabola showing in the top right quadrant. It's an opening upward parabola, and it never touches the x-axis. We can then be sure that our domain values are not restricted by the values in the denominator. The only way we could get numbers that would be undefined in the denominator would be by finding values of x that are imaginary. These are the only values that would restrict the domain. So we can again say the domain is all real numbers from negative infinity to infinity. And then you could also, just to be sure, you could also say withholding any complex numbers. Let's take a look at f of g of h of x. It just keeps getting more intense the further along you go. Start with our outermost function because it's easiest to work from the outside in, shell-wise, and so my outer shell is f of x. So I'm going to write f of x with open spaces wherever I had x's. Then I'm going to substitute g of x wherever those empty spaces exist. But remember that I also have to substitute h in. Since g of x is x squared, I'm going to set up another set of parentheses inside my first set. I have to raise it to the second power because it's x squared. And now I can substitute x minus 3 into the open space. This definitely takes practice just to get used to all the different steps. In the numerator, we will have x squared minus 6x plus 9, foiling out the numerator. In the denominator, we will have, I'm just going to leave this as x minus 3 to the 4th power plus 8. Again, a good way to check to see if the denominator will cause any undefined values is to graph the denominator in your calculator. So I have graphed the denominator in y sub 1, and when I look at the graph, again, it is in the first quadrant, it is an opening upwards parabola, and it never crosses the x-axis, which means there are no values of x that will make this function 0. So we don't have to worry about restrictions on our domain again. These are all quite nice, actually. So again, the domain is negative infinity to infinity.